Hello Physical Science, this is Mr. B, and we're continuing on with section 3 here. Again, focuses around measurement, and we talked about, again, the scientific notation as one way of kind of working with different measurements that we might obtain that are either too small or too large to write out. So that was our first part of measurement. Now we're going to actually look at, starting in this part of the section, is what units do scientists actually use for their measurements. So do we use something, because I know in our everyday life we use inches and feet and yards and things like that, but that is actually going to be different than the units that scientists use. So scientists use a set of measuring units called the SI, or the International System of Units. So I would make sure I have this written down. And SI is an abbreviation for the French International System of Units. It's like Système International des Units, I think. Again, I took French in high school, but it's been a long time, so I'm not going to tell you exactly how that's pronounced. So it's a revised version of the metric system, originally developed in France in 1791. So it is really similar to the metric system, which again you maybe heard of, like things like meter versus centimeter versus millimeter. So it's really similar to that, but it is a slightly revised version. And the reason why this is important is because scientists around the world use the same system of measurements so they can readily interpret one another's measurements. So what that means is that if we perform an experiment here in the United States, we use the SI units. Then we send our results over to maybe someone in Hong Kong who doesn't speak a word of English. They can look at our measurements, see what units we use, and they can readily repeat or interpret our experiment because we kind of have a common set of measurements that everyone around the world can use. And again, so an example of why it is important to have this common measurement, because it says if you told one of your friends that you had finished an assignment in 5, it could mean 5 minutes or 5 hours. So again, that's kind of one of the confusing things about not having a definite set of measurements. So we always express measurements in numbers and units so that it's clear so that their meaning is clear. So again, over there on the right, we wouldn't just say, hey, the temperature's 55, because we have different units when it comes to temperature, like Fahrenheit and Celsius. So these students, to stick with the SI units, they will always use the degrees Celsius when they're keeping track of temperature. So again, continuing on with more specifically about our SI units, is that SI is built upon 7 metric units that are known as our base units. So again, it's built upon the metric system, but it's a little bit different. And again, our base unit for length, meaning what we kind of are, I would say it's our default unit, what we go to when we're measuring length, is the meter. So it is the straight, and we define length, as the straight line distance between 2 points, which again, pretty simple, just the distance from point A to point B in the straightest line possible, and then that is the meter. So anytime in the SI unit, our base unit, in our SI units, our base unit for length is the meter, and the basic unit for mass, and our definition of mass is the quantity of matter in an object or sample. So kind of a word that gets used interchangeably for mass, which technically is not the same thing as your weight. So to help you get a little bit of reference about what they mean for mass. So anytime we talk about mass, we use the kilogram as our base unit. Kilogram. So we don't use pounds, we don't use inches and feet, we use the meter and the kilogram. And here is our chart. Again, don't worry about writing this chart down now. We will go over this in class. I think the main ones you really need to know, maybe off the top of your head, would probably be these top 4, but like I said, you can maybe write these 4 down, but don't worry about it. Actually, you know what? Don't worry about writing it down now. We'll go over it more in class. So those are our base units right here, again, that we measure kind of directly, our base units. So then we have derived units, which are made from combinations of our base units. So the example is volume is the amount of space taken up by an object, and density is the ratio of an object's mass to its volume. So we don't have a direct way, again, that does not fall anywhere in these charts right here, but we're going to see here in a second that we use, again, derived, which means it comes from our base units. So when it comes from our base units, again, look, we have a meter here, and then for length. And then we go to area, we have the meter squared squared. So this is derived from our single base unit there. So these are, again, derived units: area, volume, density, pressure, energy, frequency, electrical charge, which again, you can see that they have a lot of the similarities to that first chart that we looked at. And again, don't worry about memorizing these or writing these all down, but I would maybe know, again, volume and density would be an important thing to know. And again, to derive the SI unit for density, you can divide the base unit for mass by the derived unit for volume. Dividing kilograms by cubic meters yields the SI unit for density, which is kilograms per cubic meter. And again, we will do some problems to maybe make this make a little bit more sense, because I know just seeing it up there on words isn't as easy when you actually have a problem to work out. And the example they give us here is that a bar of gold has more mass per unit volume than a feather, so gold has a greater density than a feather, which again is kind of obvious just by looking at this. Hopefully you can tell that this is more dense or has a greater density than this feather up there. So that is, again, how we have our different units. Again, we have derived units for space units, and again, we'll explain that more. And now we have prefixes that we can put in front of words, again, that kind of help us understand our units a little bit better. So the metric unit, they say here it's not always a convenient one to use, but I think that this prefix method right here, once you get used to it, makes it actually very convenient to use, because it just tells you how many times we should multiply or divide something by 10. So again, we're not familiar with these because we have not used them our entire life, but if we had been using these our entire life, I think we would actually understand this stuff a little bit better. So our examples of our prefixes is that anytime you see giga in front of something, you take it to 10 to the 9th power. And so like a gigameter would be 1 meter times 10 to the 9th. And again, ends up being a billion. So it would be a billion meters there, would be a gigameter. And if you keep going on, again, a megameter, kilometer. So those are all bigger than a meter, as you notice over here on the right. So, and then when we get to a decimeter, or a centimeter, or a millimeter, or a micrometer, or a nanometer, that's when we start moving the decimal point the other way with our negative exponents. So this is why we learned about scientific notation, because it kind of helps us work with the metric system a little bit better, a little bit easier. And again, don't worry about memorizing these all right now. I would more, again, probably have a chart for us to kind of solve things based off of that. But just be familiar maybe with a couple of these, and maybe be able to identify maybe like that giga is a billion, mega is a million. I would just write down 2 of these for the quiz probably. And so our example, now we're going to move on of how to convert. So for example, our time that it takes a computer hard drive to read or write data is in the range of thousandths of a second, such as 0.009 seconds. And using the prefix milli, you can write 0.009 seconds as 9 milliseconds, or 9 ms. So that's pretty simple right here. Again, remember, if we go back to our chart, milli right here is 10 to the negative 3, so we divide it by, we put the 1,000 on the bottom, 9 over 1,000, 0.009. Again, that's almost like a simplified way. It should be a lot easier. Hopefully we can maybe end up doing this in our head as we go later on. And again, kind of to go the other way, we can make a unit larger. For example, 12,000 meters can be written as 12 kilometers. And again, when we have the 12 km, if we want to convert that back to meters instead of dividing it, we're just going to multiply by 1,000. So it's pretty simple. Again, maybe we'll do some problems if you're uncomfortable with that. But if you have this chart in front of you right here, you should be able to convert just about anything from standard form to, or from, again, the prefix to the standard form. And again, we call these things conversion factors, which is just our ratio of equivalent measurements to be used to convert a quantity expressed in one unit to another unit. So again, our example, again, this is almost like breaking it down, really simplified, is that our conversion factor is that it's 1 kilometer equals 1,000 meters. That's what this means right here. And again, you can reverse that depending on which way you're trying to convert things, with 1,000 meters equaling 1 kilometer. And again, here's our example right here. Mount Everest is 8,848 meters. So if we wanted to convert that into kilometers, we use this first conversion factor right here. We put 1 kilometer on top, the 1,000 meters on the bottom. And again, hopefully maybe you remember in some of your math classes that when you have like term or when you have terms on top and terms on bottom, they cancel each other out, and so now that gives us, again, ends up just dividing 8,848 by 1,000, and that gives us 8.48 kilometers. So that's it for that video, and again, if this doesn't make sense to you, write it down. We'll do some samples in class, but let me know if you have any questions.